So this is the intro to Experiment 8C, the Faraday's Law lab. And in order to do that lab, you should probably understand what we're trying to get at here. Like at this point of the unit, we've done that electricity creates magnetism. So if you have a ferromagnet, its spins create magnetism. If you have a electromagnet, that's current creates magnetism. So we call this phenomenon electromagnetism. We're not terribly creative here, right? But if you do Newton's third law, that means if electricity creates magnetism, then magnetism should also create electricity. This is what we're going to call electromagnetic induction, or induction for short. An induction is where you have some sort of changing magnetic flux, and that creates a voltage in nearby conductors. This is actually enough that if a plane is flying through the magnetic field of the Earth in specific directions, it actually will create a voltage across its wingtips that pilots should know about. They need to be aware about because having a positive voltage on one side and a negative voltage on the other could mean that you get sparks or unintended electrical discharges. So if you have a changing magnetic flux, you get a voltage. So let us talk about what that means, because you're like, wait a sec, there's one of these words we haven't heard before. You should probably know what magnetic flux is. Magnetic flux, flux means flow in like Latin or Greek. Magnetic flux is a new symbol. It is a new quantity for us. Its symbol is a capital Greek letter phi, or phi, depending. Fun fact, phi/phi is a letter that has a gender. Phi is male, phi is female. Don't know why letters need gender, but okay. So, capital letter of that. And what it's defined is it's defined as like how much magnetic field moves straight through a coil of wire. It's measured in a really funny unit. The unit is called Webers. I picture ducks. Apparently, other people picture grills, but I picture ducks. Webers, like duckies with webby feet. Weber's also. Oh, Weber's a brand of grill.
Oh, okay.
All right. And this is not a thing that we're going to have to calculate tons and tons of. But how to calculate it is it's a product, right? It tells us how much field, so that's B, goes through a coil of a specific area, that's A. And when we calculate it, we're actually going to leave the angle part off. This wording, the straight through a coil wording, that is the wording having to do with this angle. Because think of it as like if I keep turning this coil, there will eventually be a time where it's so flat parallel to the field that none of the field lines go through the loop. So when we calculate it, feel free to like ignore the angle for calculations, but know that it's there. Know that with the angle, you want the angle to be able to catch all the field lines in the circle. If the circle is tilted so it misses all the field lines and none of it goes through, then your flux goes to zero. So rotating a coil can create a change in magnetic flux. And the thing is, voltage is caused by a change in magnetic flux. So if you can cause this to increase or decrease, then you get voltage out of it. Okay, so I'm going to show you a few examples before I send you to the lab. And in the lab, I want you to think about, is this making your magnetic flux larger, smaller, or staying the same? So let's say I have a rectangular coil. Rectangular coils are common because it makes one, calculations easy, and two, if you had like a motor or generator, you actually get rectangular coils a lot because it's wrapped around a bar magnet. So it'd be wrapped around a rectangular chunk of iron. So how do we calculate flux? Well, I would take the area of this square times my 0.3 magnetic field, And feel free to just drop the angle entirely. So feel free to drop this cosine theta. So that's 0.3 times 0.2 times 0.2, because that's the area of my square. So this flux is 0.012 Weber. If I want to create a voltage, like create electricity, then I need a way to make flux change. So maybe I do that by making the field stronger or weaker. Maybe I do that by making the area larger or smaller. If I can make this number change, either increase or decrease, and it doesn't matter which, if I can make that flux change, then I get a voltage. And we can actually use that to create electricity. And if that sounds insubstantial, this is the theoretical basis for 96% of all human energy production. This covers all your coal, oil, natural gas, hydroelectric, wind, and nuclear power. All of them work on this principle. They all work on this principle that if you have a coil moving inside a magnetic field, you could take its motion and turn it from kinetic energy of motion into voltage. And voltage creates electricity. A thing to be careful about is, let's say I have a solenoid, so a bunch of coils, it doesn't matter how many. Let's say I have a bunch of coils, but it's only partially in the field. You only count for flux, you know that A for area? You only count for flux the area that's in the field. So I would only count half of the area of this circle. Okay, so I'm still going to drop the cosine, make that go away. I'd have my magnetic field of 5, which is incredibly strong. I think it's something like 50 million times the magnetic field of the Earth, so it's big. In the area is half a circle, so 1/2 pi r squared. So if I wanted to make a voltage with this coil, I need to figure out how to make this amount of Webers increase or decrease. It doesn't matter which. If I can get that number to change by making the field stronger, or maybe I take the coil and move it out of the field. Take the coil and move it so the field line no longer goes through. Any change in flux that I can get creates a voltage. With that being said, I think it's time to try this in a lab situation. The only thing I found from the lab that you can't really try is you can't really try the rotation part. You can change the magnetic flux by rotating, either rotate the magnet itself or rotate the coil itself. That would change the flux and create a voltage. All the other means you can figure out in this lab. So I'm going to leave those up to you. How else can we change the flux to make a voltage?
To find out, I'm going to have you go to experiment 8C, post it in Classroom, and that link will bring you to Faraday's Law in Pivot.
So once that loads up, we're going to the Faraday simulation. So Faraday's electromagnetic lab. If that doesn't work, press the button to go open it in a different tab. Click on the Pickup Coil tab. This will give us a situation that actually looks like induction. We want to either move the coil or move the magnet to create voltage. Now, this is not numerical. This is observation only. I can tell when there's a lot of voltage because I'll get a lot of brightness. Alternatively, I can switch it to the voltmeter indicator, and I can tell how much voltage I have by its movement away from neutral. So neutral, 0 is right in the center. So right now, it's making no voltage. I can see sometimes it makes positive voltage, and sometimes it makes negative voltage. And we're going to make observations about those. So part 1, open up Faraday's simulation lab. Open up Pickup Coil. If that doesn't work, click the link to go open it in a new browser. And we're looking for either the light bulb or voltmeter to be the indicator of whether or not voltage is large or small.